Yeah, I don't know why now this happens. Okay, so I always feel I have to just remind you where we were like last time because it was like a week ago, feels like forever. But basically, just to kind of like tell you what we were doing. Right. So what I was telling you is that, like, just to give you like the first like application of like these ideas is that when you have like a simplicial complex, it could like you can have like a simplicial complex being kind of like divided into pieces or like different islands. Those are usually called connected components. Okay. And that is like involves like the idea of like like of a path, right? So if you have two vertices in the simplicial complex, then you say that you can find a path between the vertices if you can find kind of like a sequence of edges that connects them. And by connecting, I just mean that the two edges points share like one of their endpoints, right? So that you can kind of concatenate them from going to V into V prime. And like for the example I was saying, you could think about it maybe in groups of social groups of friendships, right? Where like, maybe two people are not friends directly, but they are friends through intermediates, right? Like, so they can be connected through a sequence of friendships. Um, okay. And that kind of like, you can turn that into kind of like an equivalence relation. Oh, okay. That's what's more like the oops, oh my god, where here it is. You can kind of like turn that easily, this idea into an equivalence relation, right? Which is like what you see here, or like in a sense like these vertices or nodes, if you want to call them that, they can any two of them can be connected through an edge. Oh, or like a sequence of edges. Sorry, I meant. And these other four, they also could be connected through a sequence of edges, but neither of these red ones can be connected with any of the blue ones. So you would say this is kind of like a connected component, and this is another connected component of the complex. Which again, they also can be called like path components. And so what I was explaining last week is that you can set this up nicely in terms of a matrix problem, and that's where like these Laplacian matrices come in. So in the example that we were discussing, like which again, like I was just giving you as a motivation, again, the way that those complex is assembled is kind of like organized by dimension, right? So because this one had four vertices. So therefore, like kind of like four zero-dimensional things. So they make up a vector space of dimension four. Here there were like four edges. So the edges are one-dimensional. So they make up of this vector space of dimension four. And there was like a single triangle in this complex, which is two-dimensional. So that's why the two-dimensional piece is just one a vector space of dimension one. Okay. Sorry, did you say something? Yeah. Uh-huh.
So why do we like denote that R4? Are we thinking of them as like real value vectors? Or is it just
Oh, right. Like, so the reason why I'm doing it with R4, right. In fact, like okay, like if you wanted to do this like with more like fancy notation, like which I guess I can write that in a moment later on. Like you would write them as C0, C1, C2, and the subscript just represents like the dimensionality that you're referring to. And in fact, you can do this, right? They don't have to be real valued. I'm just doing that so that I can just connect this directly to linear algebra, but they can become, there's a thing called like a ring that generalizes the idea of a vector space. So they can take values on a ring, and then and there's a lot of like technology for doing that. But if you do that, then we are moving a little bit away from the connection to calculus, which I also do want to emphasize. Like, how do you discretize like a gradient, or how do you discretize a curl? Like, what is it, the version of a curl on a graph, or like a simplicial complex? So those things are way nicer to understand if you can just like connect it to real numbers, because then like in fact there are like like you can write, for those of you who like, based on what we were talking about like earlier before like the rest came, they're like famous equations in like mathematical physics, like the heat equation, the Laplace equation, like they can all be written on a lattice or like a grid or like a simplicial complex, like versions of those. But if you kind of like work in this like more level of generality with rings and other stuff, then some of that is lost just, because there's, like you have to be, it just becomes a lot more algebraic. Here I'm kind of like trying to play more on the just like regular stuff with real numbers that you know of. But you can totally do this with, you can even do this with complex numbers, like for example, I guess. But yeah, you can do this like with the integers. So, where the entries are all like integer value and things like that. But then it's not as connected to multivariable or like to just like regular linear algebra, which officially were the only requisites for this class. So that's why I'm just like, you know, you really need to take kind of like modern algebra or like abstract algebra first before you kind of like do this like in a more general setup. But that's one of the reasons why, yeah, like the correct notation for this is like C0, C1, C2, um, which I will probably write down at some point, like, just so everyone sees it. But I do want to kind of keep it very concrete where you just think about them if you want it as R4, R4, R. But yeah, like so, and yeah, like the point is that these maps or like maps or functions or linear transformations, like they are really like matrices. That's the only thing that I'm kind of like sticking to the traditional notation because this is how they are denoted. Although we are more used to matrices as just being called A and B, but that I do feel is important because otherwise you wouldn't be able to understand much of like if you ever open like a paper that uses these ideas, that is how you will see them written, like the names for the matrices. And so again, like the point is like these matrices just give you the boundary of like the objects. So again, like the boundary of an edge, in a sense, the boundary of an edge are kind of like these two endpoints, and the boundary of a triangle, right? The boundary of a triangle are its three sides. So that is what these maps or like matrices are supposed to compute. So what I was telling you last time is that even already focusing at the kind of like at the most basic level, where are you again? Oh my God, like here. Oops. Even if you just focus on this level where like you start with something one dimensional, right? If you start with something one dimensional and you produce something zero dimensional, already that level is interesting. And that's what we were talking about, like with this Laplace matrix. So again, the idea, where do I have this here? Oh yeah, yeah. Here it is. Here you were. Yeah. So the idea is that again, there's in a sense kind of like a Laplace matrix that you can define at each dimension or at each level. But again, at a level zero, right? The idea is that you can use like this matrix. So if you use a transpose of the matrix, you get back to the level of edges, and then you can use the matrix again to go back to vertices, which is corresponds to this piece. And the other one, like, it's kind of like the one minus one dimensional thing that I was telling you last time. You just put it as a zero vector space so that it kind of like this piece like looks identical to the other pieces in the other sequences for the different dimensions. But the point is that in this case, this does simplify because the green stuff is just like the zero matrix. And so for the zero dimensional part, the Laplacian or the Laplace matrix is just like this quantity. Okay, so again, this is going to be a matrix of the same size. Its size is the number of vertices times the number of vertices. So it's going to be a square matrix, which is symmetric. And I'll actually use some of the properties of it being symmetric a little bit in a moment, just to connect it to Fourier series. Like that would be useful after I'm done with this explanation. But it's going to be a symmetric matrix whose size is the number of vertices. Okay, what I was telling you, again, kind of like the philosophy of the course, is that these matrices are supposed to capture kind of like information about the complex or the space that's kind of like topological in nature. And so because this is like kind of like the matrix at step zero, this is related to that, like sometimes what people call like zero connectivity of the complex. So that's just like like the part of, like of whether you can be separated by a path or not, which is what I was going to finish showing you of today. So my claim, which was what I was proving last time, and I will finish off today, is that if you compute the null space of this matrix, again, the null space of a matrix is a vector space, and because it's a vector space, it has a dimension. So the dimension of that vector space counts the number of path components of the matrix, or like the not the matrix of the simplicial complex, or it counts the number of connected components of the simplicial complex. So again, like it's always useful to just be concrete and think about what this is saying. So like if you go back to the social network analysis, right, like analogy of like friends of groups of friends, what this is saying is like it's counting like how many groups of friends there are. And again, by groups of friends, I mean it here not that everyone is a friend with each other within the group, but at least we're all connected through friends within the group, right? Or like in a more silly case, like like the if you look at it, like the network could be like all the US undergraduate students, right, like all the undergrads in the US, right, and so the relation could be belonging to the same university, right? So in this, which is okay, that is a better example, right, because usually you don't make you are not a student from two universities simultaneously. I don't think anyone there's a single example in the US of someone like who's enrolled in two universities. That's probably, I don't know if it's even allowed. So like so you could create like a network. You could imagine like a network where, again, you draw an edge between any two students that belong to the same university. And then that there you have like this abstract network. It would have tons of vertices, right? Like there are probably millions of undergrads in the US at any given year. Um, and then what I'm saying is that, oh, you can associate to the network a matrix, and the dimension of the null space of that matrix would give you the number of universities in that case, which is kind of like crazy if you think about it, like you can just do it in terms of linear algebra. The point is that the other matrices of the complex, this is called like a complex, but there's kind of like a one-dimensional Laplace matrix, a two-dimensional Laplace matrix. They kind of give you more information about how things are connected. So the one-dimensional Laplace matrix gives you more information about holes and like in the complex. In again, if you thought about it more like as a space, but that will, I'm starting with the zero-dimensional piece because that's kind of like the easiest one to understand at a visceral level, because it's just like the kind of like the things that can be connected or not by a path. Uh, which again, like when the complex has like millions of entries or like vertices, it's not super obvious to that you could. I mean, there's no way really to just see that by naked eye. So, but yeah, so like that was my claim, and the proof is kind of like, again, it was worth going in my opinion just because it has some interesting linear algebra ideas. So again, just to kind of like give you like a 2-minute summary of what we were doing last time. So if something was in, what does it mean for something to be in the kernel? That you satisfy a homogeneous equation. It's just that because this matrix happen to have this particular form, you can rewrite it this way. And again, if you play with it, what we found is that this meant that the vector had to be also in the null space of actually this part of this smaller matrix. Okay, so again, the matrix L0 is kind of like a product of two matrices, but because of the shape that L0 has, being in the null space of this matrix is the same as being in the null space of like one of the pieces that makes it up, which is like a useful, a convenient thing. So really, what you had to understand is just the null space of this matrix. And what I was telling you last time is that to find the null space of this matrix, you have to find a formula for it. And that's kind of where we ended up discussing last time. So the formula uh, for this matrix, and this is kind of like where I'll start today, but the formula for the matrix was that if you have oh my God, like I hate how this app sometimes moves. Okay. So the formula was that if you have a vertex, again, the idea is that this matrix, if you feed as input a vertex, it has to produce some combination of edges. Okay. And so which combination of edges does it produce for a particular vertex? It produces a sum of all the edges that end at that vertex minus the sum of all the edges that start at that vertex. Okay? So it's kind of like what this matrix detects is kind of like the all the edges that somehow either end or start at that vertex, and it kind of like takes a sum of those. So for example, there's a picture that I ended up like with last time. If you think of the vertex B being that one, you see there are three edges, the red ones that terminate at V, and there are two edges that start at V. So we are kind of like the way this matrix is being computed, it does like the edges that end at V minus the edges that start at V. And that's you know, that will be how it's defined. In fact, I don't know if you remember from multivariable calculus the divergence of a vector field, if that rings a bell, but it is kind of like a similar idea to the divergence, which I actually will make more precise later on. Because if you remember like the divergence, like the divergence theorem from Gauss and like, was like, how much stuff is going through a particular surface. And this is kind of like a version of that, but of smaller dimension, because if you think about this as kind of like a fluid, like where these edges represent water, then there's some edges are kind of like being sucked in by the vertex, and there are other edges are being pushed out by the vertex. So it's kind of like absorbing and like it's kind of like absorbing and like at the same time destroying like some sort of substance. And when I go to this ranking stuff, like this Hodge statistical ranking, that actually is going to be like a useful analogy to have. But so yeah, that is more or less like a summary of the situation. Is that making sense so far? So good. So like, let me just to continue here, I will. Okay, so now we have like a formula for this matrix. I'll copy paste it into the new notes. Okay, so again, this was what we had last time. So the goal for today is just to understand the null space of this matrix. So the goal is to understand the null space of this matrix. Again, what was this matrix? Like this matrix starts in a vector space determined by the vertices. And that's the input. And it ends in the vector space determined by the edges. Okay, so it's again, like you can kind of like see it in this formula because I fed a vertex and I produced some edges. So it goes from the space of vertices into the space of edges. That's how you should think about what this transpose matrix does. Okay, and so what does it mean to be in the null space? Being in the null space means that you solve the homogeneous equation. So let's suppose that let's suppose that you have like a vector that solves a homogeneous equation. Now, and this is going to now finally be related to something I had mentioned before. Again, where is this vector living? This vector is living in the vector space formed by the vertices. So it is it is a sum of the vertices, kind of like what I had called a formal linear combination. So notice, that this vector can be written as a combination. Well, I don't know if it's just like a combination of like a formal linear combination of the vertices. So it's just like each vertex times a coefficient. So there is a very concrete way to think about this, as I had told you before. You can literally think of this as a function, okay? maybe just to do it like more diagrammatically, like just to go back to this, if just to go back for a moment to this like simplicial complex that I had last time, just to copy paste the picture, you know, if this is my simplicial complex, um, then what is an element, in this, like in this vector space that I was telling you about? Like an element, a vector could be something like 3v0 minus v1 plus 2v2. Okay, well, because there's nothing plus 0v3. So like, like the coefficients can be like any real number, right? So they're not necessarily like, they don't have any restrictions. So that is a combination of vertices, as you see there. The point is that you can represent that as a function, okay? Because again, like you can think of three as the value of the function at that vertex v0, and -1 as the value of the function at the vertex v1, and 2 as a value of the vertex v2, etc. So if you wanted to draw this more diagrammatically, the way to, and kind of like more like as kind of like almost like a graph notation for the function, you could just like imagine, let me put it like this. I could draw kind of like some sort of like vertical, almost like a tower. I mean, this is not going to look that great, but because, oh, actually, let me draw it like this. I will, not that you have to do this, but let's see if this works out nicely. Oh, yeah, yeah. Okay, this is going to look much nicer now that if I do it like this. Like kind of like how you see functions in calc, how you represent functions in calc 3. This will make it easier for me to relate this to signal analysis in a moment. So that's why I'm also trying to do it this way. So, one way to kind of like think about this as a function is, again, kind of like each of the coefficients is kind of like the value of the function of one of the vertices. So I can just draw kind of like almost like a vertical tower, kind of like the height, right? Kind of like it's in Calc 3, where you're plotting the graph of a function. So at v0, the height is 3. At v1, the height is -1. Okay. At v2, the height is 2. And at v3, the height is 0. So you kind of like stay where you are, right? So it's kind of like, at each vertex, like you can think about it kind of like, again, like maybe there is some like you put like a sensor at each vertex that has some intensity, like kind of like a signal, and the value of that signal is like kind of like the value of this coefficient. That's one way to think about it. But so from that perspective, so if instead of like writing, so in this way you can think of this as being like, in this example, it would be kind of like f of v0 times v0 plus f of v1 times v1 plus f of v2 times v2 plus f of v3 times v3. And then it makes sense to call, in a sense, like you could call that like a function on the nodes or the vertices, because it's an assignment of a number to each node. You assign to each node a number. Okay, that's kind of like the strength of the signal, whatever signal you're thinking about at that node. Okay, making sense. And then, but again, that's a little bit of interpretation, which again will be useful in a bit later. But the idea with all of this is that if you just to go back, okay, so again, if this is zero, if you have a vector in the null space, you that means that that vector solves the equation, the homogeneous equation that you see written there. And so what I'm going to do, as before, is that I will kind of like take dot products on both sides of the equation with an edge. So I'll just write for now like an edge as being E. Okay. So I'll take the dot product of this equation with an edge. Again, that's something you can do. The point of dot product is that it's nice because a dot product turns everything into a scalar. So even if you started with the vector equation like we did, once you take the dot product, you get a scalar. So let's just work out a little bit what this is in more detail. So again, like this vector was, this sum of coefficients, but again, I'll just kind of like use the function notation just to emphasize that out a little bit more. So again, instead of writing the coefficient as Ci, I'll write it as f of bi, because I'm thinking kind of like of it as of these coefficients as making up a function, as I was telling you. And the dot product of anything with the zero vector is just zero. So now you have that this dot product has to be zero. But again, the matrix is a linear transformation. So like it only, like you can kind of like move it inside the sum. That's how like, linear transformations work. So you're really just doing this thing. Is that okay? So far, so good. And now I'm going to apply the definition of this matrix to each vertex. Again, what does, now we're going to get a little bit bogged down by notation, but what is this supposed to do? It's like when it's acting on a vertex, it just gives you a sum of all the edges that um end at that vertex minus all the edges that started that vertex. So let me just first, like, let me take out again, because the dot product is also kind of like linear. You can use a distributive property, so you can take out the sum here, and you're just doing this thing. So I'm doing all of this before evaluating the matrix at this vertex. But now I'm going to write down what this was. So again, this thing is going to be what is this? This is a sum over all the edges. Okay, I'll write them as E prime. All the edges E prime that end at V I minus a sum of all the edges, which I will call E double prime, that start at VI. Have I said before like of this Kronecker delta or have I not? Have I used the Kronecker delta before? Like the one that delta IJ, have I? I don't think, okay, well, I mean, without saying it, like, um, so, okay, these distributes because this is a dot product, right? Like, so the dot product, you can distribute it. So you really, what you're doing, so this becomes a sum over I of f of vi of what? Of E dot E prime. Yeah, I don't think there's so many class, when you're teaching for different classes, like you don't know which class you're get saying something like, and then like, and they're all sometimes there's some non-trivial overlap between the classes. So I'm like, okay, which one did I say this or not? Okay, let's see. Did I end up doing? Let's see. Actually, is this going to be easier? Actually, okay. This is going to be a more complicated route. Okay, so I'll take it back. So I still have here, now that I check in my notes, like the way I'm doing it in my notes is a little bit easier. This is annoying, but okay, I use the prop, it will make it more clear for how I want to explain this. So I use the magical property of the transpose. So I move the matrix to the other factor as a transpose. You see, like always, not, you have to think of want to use this or not, but otherwise it becomes too cumbersome, like the notation. So like it will be easier to keep track this way. And what you have to remember, yeah, this is much easier, is that this edge E, because otherwise I have too many sums. This edge E is just some edge, right? So the edge E, it just goes from some vertex, which I'll call V prime, and some other vertex that I'll call V double prime. Okay. And so the again, like what this matrix is supposed to do to an edge is to compute its endpoints. So the endpoints of this edge are V double prime minus V prime. So this will become a sum of f of vi times V double prime minus V prime. Yeah, this is a little bit easier. Now, if I do the distributive, use the distributive property of the dot product, this would become V double prime dot VI minus V prime dot VI equals 0. Okay. And then, well, oops. And then, well, this is like, you use a distributive property. So you do this one times this one times this one, and then you just move it, move the one with the minus to the other side. So you end up getting this. Okay, so far so good. Questions up to this point. So again, like I have just summarized what I just did. What I'm saying is that if you have a vector, you know, just to go back to the very beginning. So what I'm saying is that if you have a vector that's in the null space of this matrix, then this equality must be true. So it must be the case that this sum over I of these quantities equals this other sum over I of these other quantities. Okay. Now, this is where you have to think a bit about where the sum is taking place. The sum over I the sum is running, the index I runs over all the possible vertices, right? So eventually, because this goes over all the possible vertices, you have to remember that the vertices are kind of like an orthonormal basis. So almost all of these dot products are zero except one of them. Okay, so this sum basically disappears except for one. That's where like this Kronecker delta comes in handy. Maybe I should put it here because I may need it at a different time. So usually how you would write this is like this is delta of V double prime VI. And that means that that's exactly one if the two coincide and zero otherwise. So this is one if, and this is called a Kronecker delta, super useful notation. So this sum is only this that product gives you one exactly if the vectors are the same, or the vertices if the vertices are the same, and it gives you zero if the vertices are distinct. And same with the other one. This is also like a Kronecker delta, but now between V prime and VI. So the point is that this sum, it is not such a complicated sum because the only thing that survives is the term where V prime equals VI. So that means that you can replace f of bi here with the f of b double prime, and you can replace f of bi here with f of b prime. So what that means is that f of b double prime equals f of b prime. Is that okay? Is that okay? And this is actually like an interesting thing. I have to say what that means in a moment. Um, but what that means is that uh, and again, here B prime and B double prime were just like the vertices or the endpoints of that edge. But what this is saying is that and this is why I wanted to use this function notation. What this is saying is that if you think about it as a function, that the value of the function must be the same at the two endpoints of the edge, right? So let me write it down. Let's just think about what we just proved here. So what we just did is that therefore, if this quantity, right, is in the null space, what that mean for that to happen, oops, sorry about that. For that to happen, for every edge in the complex, right? For every edge in the complex, again, I'm thinking of an edge as kind of going from one vertex to another. We must have that f of v prime equals f of v double prime. What does that mean? It means that the value of the function is the same as the endpoints of the edge. So at the endpoints of this edge. Is that okay? Is that making sense? And how is that useful to disconnected components? Like, let me actually put back the picture that I had drawn last time, where like there were like two connected components. Oops, sorry about that. So again, like just to think about it in terms of like a function notation, right? Like you can think of an element in the null space as a function that assigns a value to each vertex. So imagine that I assign the value to imagine that I assign the value 2 to this vertex, right? So what I just proved is that if the function that assigns a value to this vertex is going to be in the null space, then it has to be assigning the same value to the other endpoint of this, like to this other vertex, because these two vertices are connected by an edge. So that forces this other vertex to have value 2. Okay. But then this vertex is connected to this other vertex through an edge. So that forces it to have this value too. So you see kind of like the being constant is kind of like propagating throughout, that a connected component of the graph. And this also gets forced to be 2, this also gets forced to be 2, and this also gets forced to be 2. But there's nothing like, again, so just by starting by assigning a random value to one of the vertices, that kind of like gets propagated across the path component, because by definition, in a path component, everyone is connected by a sequence of edges. So if the function is always coinciding at the endpoints of each edge, that kind of like just like goes through the entire graph. So in the function, if you go back to this example I was giving you with the networks and the students, where I was saying, like you could imagine that you have a graph where the nodes are the students, and like the components, like the connected components are belonging to the same university. So kind of like the function in this case could be kind of like giving you the ranking of your university. Like there are always like these undergraduate rankings of like best 50 colleges in America or whatever. So like all the students, if they belong to Rutgers University, if Rutgers is ranked like 50 or 60 or 30 or whatever, they would all be assigned the same number, right? Actually kind of like goes throughout the entire network in a sense. But here, this could have been 2, but it didn't have to be 2. It could just be 3. But the moment this one is 3, it forces the others to be 3 and 3 and 3. Okay? So basically, what I'm trying to say is that this function kind of like essentially, like there will be this function f takes the same value on each connected component. That's kind of like the idea. So let me write this down in a nicer way. So what this just proves, so this just proves that if f is in the null space, that if the function null space of the matrix L0, then this function f must assign the same value to each connected component of the Simplicial complex. Is that yes?
Well, we have that like each connected path has its own unique function value.
Well, that's that right. Like that's the thing, right? Like the thing is, like I can think of these, right? I can think of the function that assigns two to this sub connected piece and three to this other connected piece as two times the constant function one, right? Like so each connected component has kind of like sometimes that's called like an indicator function that's one at that component and it's zero elsewhere. And that's also why this is like useful from like a signal analysis perspective. Yeah, I'm glad that you asked me that because that kind of like okay, so let me just draw down you know. So let's call this piece A, right? And this other piece B, right? So what I'm saying is that each of the connected components has kind of like as like a unique signature function, which is like the one that gives one to it and zero everywhere else, right? So you would have like this there would be like this function which I'll just call f sub a. So f sub a just gives one, 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 and one here, and it assigns 0, 0, 0, 0 to the others, right? So I'll call this function f sub a. So this is like the function f sub a, right? It takes value 1 on the connected component A and value 0 everywhere else. And then you would have like a version for that, but with the roles flipped, right? And so hopefully this is how you can see how this might be related to signals and other things, because like of these assignments of values, like again, if you thought about this as a network with sensors or something of that sort, so like I assign value 1 here, 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 and now this one assigns value 0 everywhere here, and this is like the function f sub b. Okay, so for example, the one that I was working with, right? Like the one that I said, well, you could have a function, you could have a function like that maybe assigns value 2 to component A and value 3 to component B, right? So if you had like this function, right? If you had this function f is just 3 times, right? Sorry, it's 2 times f sub A. Oops, sorry about that. It's 2 times f sub A plus 3 times f sub b. So it's a linear combination of these indicator functions. So the indicator functions are kind of like a basis of constant functions on each connected component. So they are that's why the dimension of the null space will be the same as the dimension of the number of connected components. Any probability theory, someone takes probability theory, like the indicator functions, like they're also used there as a lot, like for because sometimes it's just like easier to like the independence condition of events. It's just like the probability of any what like A given B is like the same as probability of A times probability of B. Like the condition of probability, conditioning, if two events are independent, conditioning on one event doesn't make a difference, you know. Um, so, or like, sorry, like the probability of A is the same as the probability of A given B, and that forces the probability of the intersection A intersect B to be probability of A times probability of B. But the point is that you can write it very nicely in terms of indicator functions. It's very elegant way to do it. And so all that I'm saying is that it's kind of like an analogous thing here. When you have a simplicial complex, you can create a function that's exactly one on each connected on a particular connected component and is zero everywhere else. And those are kind of like a basis for the null space of this Laplacian matrix. Um, so, so the idea is that when you have a connected component, sorry, a simplicial complex for each connected component, you can define an indicator function. That's how they're called, an indicator function, which equals one, which assigns the value one to each node in that connected component, or let's just use the word vertex of this connected component, and zero to all the other vertices, and zero to the vertices of all of the remaining connected components, which belong to the other connected components. And the idea is that it's kind of like easy to see because they're like exactly ones only on a component at a time, that they are linearly independent and that they form like a basis for the null space. So these functions form a basis. But there is, but this means that the dimension of the null space is the same as the number of the connected components, you know. But that means that the dimension of the null space is the same as the, isn't that nice? I find this very nice. Uh, You know, like it's not like a terribly complicated proof, but I think it's worth going over it because it has like very useful ideas, and you know, where also like a situation where like you can develop a lot of intuitions, you know. Um, that making sense, kind of? Okay, so let me give you some analogies with the Fourier series, Fourier like analysis. So that you see that this is actually, and now what I'm going to do is justify that this deserves like the name of Laplacian. So why have I called these Laplacian matrices? So I'll tell you why this deserves this name. Okay, so why is this called like a Laplace? Why am I calling these matrices Laplacian matrices? Why are these matrices being called Laplacian matrices? Okay, so let me start with what people call like the Laplacian in calculus. And I'll do it for functions of one variable. So if you have a function of one variable, so you could have done this in Calc 1 in principle. You don't do it, but you could have. So there's a thing called the Laplacian. Uh, and they denote it kind of like by just like a regular triangle, not to be confused with the when you put it upside down, that's the gradient, right? Like it is confusing at first, but you know, but the idea is that the Laplacian of a function, you know, if you apply the Laplacian to a function, what it produces is just well. typically, um, it just like it just in because it's like a function of one variable, it would just like be the second derivative with respect to x. If it had been like a function of two variables, it's like the sum of the second partial derivatives. So for like maybe I should write it like for like if you had like for example a function of x and y, it's like the Laplacian of this function would be the second derivative with respect to x plus the second derivative with respect to y. And if you had a function of two variables, it would be the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. So if you have in general, a function of x1, x2 up to xn, right? Its Laplacian is the sum of, like the second order partial derivatives. Okay. So sometimes it is a little bit better maybe to just like express it out in this way. Um, yes.
It's like the diverge.
Right. Like it would be the divergence of the gradient, right?
The gradient.
Yeah. Yes. Like for example, right? Like you can write this like in Calc 3, right? Like this would be like the divergence of the gradient of the function. Now, what I was going to say is that is there are two conventions for the Laplacian. So this is what you would call like the PDE convention, PDE for partial differential equations. Then there's like the geometry convention, which is the one that actually is more closely related to what we are doing here. So the geometry convention is the same one, but you just put a minus in front of everything. So in the geometry convention, you put the Laplacian, you call it minus the second derivative with respect to x, or minus the sum of the second order partial derivatives. And there's like an advantage to doing it that way, which I'll show you like in a moment for why you would put the minus in front of it. But so again, like you just have to be careful about that because it depends on whether you're opening a book in probability theory, like PDEs or probability theory versus a book in differential geometry, like whether you have like the minus or not. And then like there's like and then there's like the heat equation, which is like kind of like a, kind of like the Laplacian appears there, but now it's kind of like the derivative with respect to t equals like the Laplacian of a function and other things. So the Laplacian appears in many different setups, like the Laplace equation. That's kind of probably the most basic one. But I'm just going to stay in the case of one variable because that's already enough of like an analogy. So the idea is that you can think of, regardless of the number of variables, the Laplacian is kind of like a linear transformation. So the Laplacian is a linear transformation, meaning that if just because that is inherited from the fact that the taking derivatives is linear. So like meaning that the Laplacian of f plus of f plus g is the same as the Laplacian of f plus the Laplacian of g. Okay. And then if you had like a constant, like you can take out the constant out of the function just because this, again, it's like a property that gets inherited from like how like derivatives work in calculus. So there is a sense, right? There is a sense in which the Laplacian is some sort of like matrix, but it's more like an infinite dimensional matrix just because if the variable is continuous, like if you actually wanted to write it down as a matrix, it just ends up having like infinite rows and infinite columns. But like in a sense, like you can think of it as some sort of like matrix. So in that sense, the Laplacian is an infinite dimensional matrix. Now, like for example, if you had a function of one variable, now you can, okay, so then you can you can study the functions that are in the null. So if you think about this as a matrix, you can think of what is the null space of the Laplacian? So the null space of the Laplacian, so let's think about that. The null space of the Laplacian would be the functions that satisfy that the Laplacian equals zero, right? Because like a null space is like a homogeneous equation. So it's just that in this case, homogeneous means being set equal to zero. And those functions are very important. They're called harmonic functions. So this is called, if a function satisfies that it belongs to the null space of the Laplacian, they are called harmonic. So these functions are called harmonic. Now for functions of one variable, they're not that interesting. They're super easy to understand. Like for functions of two or three variables, like if you open like an electromagnetism class course, like textbook, you will be spending a lot of time just solving like the Laplace equation, or just finding harmonic functions. So they are like a very traditional part of mathematics. But just to kind of like at least show you what are the harmonic functions in one dimension. So for a function of one variable, what does this become? This just becomes that minus the second derivative with respect to x of that function has to be zero, right? Well, and you do know kind of like this answer, right? Which functions have second derivative equal to zero? So which are those? Which ones have second derivative equal to zero?
Polynomial under the be like two or whatever.
Well, right, but what is the name for the polynomials under degree two? Right, right. Like they are literally linear. Right, right. Like, I mean, and you can kind of like find that by integrating twice this equation. If you integrate this one time, right, like that tells you that the first derivative had to be a constant, right? And which I'll call C0. And if you integrate this one more time, that tells you that the function had to be C0 times x plus another constant, right? So in fact, like the solutions to the harmonic functions in one dimension are just linear functions, which again is not super interesting because it's in one dimension. But once you get to two or three dimensions or like more higher dimensions, there are tons of it is more interesting than that. In fact, this is very related to complex analysis and other things like so. But in one dimension for a function of one variable, so functions of like the harmonic functions of one variable are simply the linear functions. Okay, so far so good. Is that making sense? Now, uh, and again, like I'm finishing writing the problems for the assignments, but as I may have, I think I told you this one day that one way to think of a circle, right? One way to think of a circle. Oh my God, I have so many cables. Let me use which one can I use here? One way to think of a circle is just like an interval where you connect the endpoints, right? So one way to think of a function on a circle is a function on an interval where that agrees on the endpoints. And that can allows you to, once you have a function, if you have a function, imagine that you had like a function defined on an interval, like 0 to 2 pi, just for like convenience, right? If you had like a function, oops, imagine that you had like a function on the interval 0 to 2 pi, right? It can be whatever it wants to be, but you're forcing it to agree at the endpoints, right? Well, once you do that, you are allowed in a natural way to just extend the function to the entire number line, right? Just by copy pasting it. And if you do it that way, you just created a function which is periodic of period to pi, like automatically. So essentially, like the functions that are periodic are connected to the functions that are defined on the circle, right? So one way to think about a function defined on a circle is just as a periodic function, like that's kind of like the idea. So once you have a function, if you have a function defined on an interval, A comma B, and the function satisfies. Okay, I'll just write a couple more ideas and I'll continue this next time. Um, it satisfies that f of A equals f of B, meaning that it agrees on the endpoints, but you can extend that function to the entire number line just by copy pasting it, and that makes it a periodic function, then you can extend it, extend this function to the entire number line and it makes it into a periodic function. And this is very common, like you'll see that in, like, again, if you ever take Fourier series, like, so like there's like this, I can think like it's called the sawtooth function. Where are you? Yeah, like these are kind of like very common ones where you just have like a signal, and this is nothing like fancy, right? It's kind of, again, kind of like a line, but well, this one doesn't agree at the endpoints, but like, yeah, they're fixes. And yeah, actually, do I have one that I don't have? Oh, like, I guess, well, like, actually more like these like rectangular signal. You can kind of like play, like if you play with one of these, right, like, depends on where you are. Yeah, yeah. If you take one of the triangular signals, again, like, you can just copy paste it, and then depends on where you cut the interval, and you could just think about it as agreeing on the endpoints, and many of these like do just naturally give you functions defined on the circle. That's my point. Um, okay. Oops. And so, from this perspective, just to kind of like get to the punchline, the idea is that if you look at, now here's interesting. This is interesting. So if you try to impose the condition that the function is periodic, right? Those that are happen to be periodic and harmonic, that kind of kills off the linear, the part that depends on x, right? Because if you sketch, like the graph, and we just said that the graph of a function that's, you know, the function that a function that's harmonic has to be linear, right? But if you want it to be on top of being linear, in addition to that, you want it to be like periodic, like, you cannot have like an x dependency because like the x variable is not dependent. So what that means is that the functions on the circle, oh, and sorry, I forgot to write that down. And in this way, regarded as a function defined on a circle. So the functions on the circle, which are harmonic and period, so so the functions which are harmonic and periodic are exactly the constant functions, okay? Are exactly the constant functions. In other words, like the only harmonic functions on a circle are the constant functions, okay? So the only, because again, like a function that's periodic, it lives on the circle, and if it's harmonic, it has to be constant because it cannot have the linear term. But you see, like being constant is related to this thing. What I'm saying is that in the case of the circle, like harmonic functions are constant, and being constant is kind of like analogous to what I was saying, that the function had to be constant on the different path components of the simplicial complex, right? Now, the analogy is a little bit stronger than that, but I'll continue this next time. But when you have a matrix, what you want to understand are its eigenvalues, eigenvectors, if the matrix happens to be symmetric. Oh, well, or even just like a square matrix. Once you have a square matrix, you want to understand eigenvalues and eigenvectors. But so basically you can try to understand the eigenvalues and eigenvectors of the Laplacian. And so what would be an eigenvalue of the Laplacian? It's just like a function that satisfies this equation. Because remember, what is eigenvector equation for a matrix? It's A times V equals lambda V, right? So this is the same, it's just that the Laplacian is working as, the Laplacian is working as our matrix here. So if you put this here, so what does this mean? You're trying to find now functions whose second derivative equals minus that function times a constant, right? So what are some functions that you know of that if you take their second derivative, you get minus that function times that is like a sine or a cosine, right? If you take a sine or a cosine, you get a minus from the cosine, like cosine derivative of cosine is minus sine. So in fact, kind of what happens is that the sine of k times x or cosine of k times x, where k is a constant, right? Those satisfy this equation. And again, the one of the assignments will ask you to just check that. But something like this would satisfy this equation provided the lambda equals k squared. So it has non-negative eigenvalues. Like that's why the minus is useful in this case. That's the main reason for having like the minus in the formula of the Laplacian, so that its eigenvalues are non-negative. So that is what people call like a positive semi-definite matrix. Which is kind of like the kernel matrices and all the other things. Like if you've ever heard of kernel methods, um, provided lambda equals k squared. But then the idea is that in the same way in which, well, the point of Fourier series, which I'll tell you more about it next time, is that any periodic function can be decomposed into a series of sines and cosines of different frequencies or different modes. And the idea is that if you have any function defined as a simplicial complex, it can be decomposed in terms of like a sum, now a finite sum, because there's no more like everything is finite in our case, of the eigenvectors of the Laplacian matrix. So the eigenvectors of the Laplacian matrix will be the discrete analog of sines and cosines. So now you have like a version of a sine or a cosine on a graph or like a network, which is kind of like a very interesting thing to do. And so when you have like a signal, I'm rambling because like I still there's so many things to say, but like they're like, if you have ever done like Fourier transforms or things like that, when you take a derivative with respect to time, that gives you frequency, like like there's this time space and frequency space, and there are certain things that you can do in one space, like that transforms into the other, and then there's kind of like all the versions like of all of those things for like graphs or simplicial complexes. But I'll tell you more about that because I'm over time. So let's finish here. But I'll mention some analogies next time because I think they're kind of like useful analogies to have around. So let's end here. I hope it stopped raining because I don't want to. I think it's not going to be that bad when I take the weather. I don't like the weather app.